Alrighty, as soon as I get the lecture open, we can go ahead and get started. I obviously have not done your exams yet. I will hopefully grade them over the weekend, and then you'll have that feedback. So today, what we're starting with is talking about how to lie with statistics, because you can. And so we're going to be getting more into the nitty-gritty of interpreting things. That'll help you be able to see the screen a little bit better. And I am going to take a second just to take attendance before I dive on in. Go. Toggle our captions, and then we'll get going here. I think everybody is probably just feeling a little slow, feeling a little blurred today, because it is just a yucky day and gonna get yuckier, I think. Alrighty. And then what I plan to do is at the end of class today, give you some time to finish up the assignment about bias and sources that we started at the end of class on Wednesday. All right, so this was something I found when I was prepping this class 2 years ago. I know it's always fun to find stuff, just sort of stumble across stuff that makes you think about class. And this was something like this. And I sort of thought this was amusing and also aggravating. So this was the, I believe, Twitter post. Kyle, 28, has already paid off his student loans. Going to go enroll and prepare to retire at age 40. Senior spending is difficult, he says, but if I can do it, anyone can. Learn how he did it. So then you click on the article, and he's got his first job at his dad's office, and made $250,000 a year at that first job. To save money on housing, he lived in his grandfather's empty vacation home. I don't know about y'all. My grandparents don't have empty vacation homes just sitting around, right, for me to be a part of. And then he also used his savings and a $500,000 gift from his uncle to purchase his first home. Must be nice, right? And so the whole idea here that this person, he hacked it, right? He figured out the way millennials and Gen Z shouldn't complain. They'll all be fine, right? And oh, poor baby, he didn't get to go on his vacations with his family to Italy or Japan. He had to vacation domestically. I don't know about y'all, but like, I don't get to vacation every year, right? And so we need to always be looking behind the story and seeing like, how feasible is this? How realistic is this, right? Because people will say stuff like this, and it's, not necessarily doable for the vast majority of the American public here. All right, and so this is a little video on how statistics can be misleading.
Statistics are persuasive, so much so that people, organizations, and whole countries base some of their most important decisions on organized data. But there's a problem with that. Any set of statistics might have something lurking inside it, something that can turn the results completely upside down. For example, imagine you need to choose between two hospitals for an elderly relative's surgery. Out of each hospital's last 1,000 patients, 900 survived at Hospital A, while only 800 survived at Hospital B. So it looks like Hospital A is the better choice. But before you make your decision, remember that not all patients arrive at the hospital with the same level of health. And if we divide each hospital's last 1,000 patients into those who arrived in good health and those who arrived in poor health, the picture starts to look very different. Hospital A had only 100 patients who arrived in poor health, of which 30 survived. But Hospital B had 400, and they were able to save 210. So Hospital B is the better choice for patients who arrive at hospital in poor health, with a survival rate of 52.5%. And what if your relative's health is good when she arrives at the hospital? Strangely enough, Hospital B is still the better choice, with a survival rate of over 98%. So how can Hospital A have a better overall survival rate if Hospital B has better survival rates for patients in each of the two groups? What we've stumbled upon is a case of Simpson's paradox, where the same set of data can appear to show opposite trends depending on how it's grouped. This often occurs when aggregated data hides a conditional variable, sometimes known as a lurking variable, which is a hidden additional factor that significantly influences results. Here, the hidden factor is the relative proportion of patients who arrive in good or poor health. Simpson's paradox isn't just a hypothetical scenario. It pops up from time to time in the real world, sometimes in important contexts. One study in the UK appeared to show that smokers had a higher survival rate than non-smokers over a 20-year time period. That is, until dividing the participants by age group showed that the non-smokers were significantly older on average, and thus more likely to die during the trial period, precisely because they were living longer in general. Here, the age groups are the lurking variable and are vital to correctly interpret the data. In another example,
And that's why when you do these types of analyses, you really try to get what they call a matched control group. So like your control group should have the same average age as your experimental group, as the group of smokers, for example.
an analysis of Florida's death penalty cases seemed to reveal no racial disparity in sentencing between black and white defendants convicted of murder. But dividing the cases by the race of the victim told a different story. In either situation, black defendants were more likely to be sentenced to death. The slightly higher overall sentencing rate for white defendants was due to the fact that cases with white victims were more likely to elicit a death sentence than cases where the victim was black, and most murders occurred between people of the same race. So how do we avoid falling for the paradox? Unfortunately, there is no one-size-fits-all answer. Data can be grouped and divided in any number of ways, and overall numbers may sometimes give a more accurate picture than data divided into misleading or arbitrary categories. All we can do is carefully study the actual situations the statistics describe and consider whether lurking variables may be present. Otherwise, we leave ourselves vulnerable to those who would use data to manipulate others and promote their own agendas.
In psychology, we're always kind of looking for what are these extraneous variables we might be missing? What is not in our data set that might explain this that we should include in our next data set? Alrighty, and then good old Bill Gates is here to tell us about lying with statistics as well.
Every summer, I try to do a little extra reading. Here's a few books I've read recently that you might enjoy. How to Lie with Statistics by Daryl Huff. Being able to understand what you're looking at and being willing to say, hey, where did that come from? Is that accurate? Being able to understand what you're looking at and being willing to say, hey, where did that come from? Is that accurate? It's a quick read. It's got a lot of good examples in it. It's a trip to the past. even though the basic points it makes are still as valid today. On immunity by Eula Biss. She explains the history of vaccination, why children who don't get vaccinated can even affect those who are vaccinated. Why children who don't.
And so that just gives you a little hint of how much work has been done in this area to try to sort of elucidate the fact that, you know, stats, as much as we love them and we love to give percentages and things like that, don't always give us the full story. So there are some lessons here on how to lie with statistics. And so one of the main reasons why this is the course we require for the psych major is that we want you all to develop data literacy. We want you to be able to read statistics, understand them, argue with the statistics, and make decisions based on this data, based on the statistics, right? And so as we just saw, doing so also implies that we know how to recognize when something might be off. And so, again, this is going to keep coming up again and again. It'll come up in your other psych classes, but correlation does not equal causation, right? It seems silly, we have to keep repeating it, and yet in the real world, people are not great about interpreting correlations. So you should view correlations with skepticism, especially if someone is making a causal conclusion based off those correlations. Again, could be that X causes Y. It could be that Y is actually causing X, or it could be that there's this third variable Z that's affecting both, and therefore X and Y are actually unrelated. Or it could be there's Z, A, B, C, and D affecting both, right? We know that humans are very complex. So you need higher level studies if we think about that pyramid that we looked at, a hierarchy, to determine causality. So you need those randomized control trials, those longitudinal or cohort studies, and you want to control for as many confounding or nuisance or lurking variables as possible. I kind of like how they phrase this one relationship, don't last forever. So you could find a correlation, but it could also be possible that that's only true for your particular sample, right? So it could be that maybe, yeah, these things are related, but only for upper class, white, cisgender, heterosexual people, right? And if you look at anyone outside that group, you're not going to find the same correlation. That's entirely possible. You could be looking at a limiting region of each variable. So part of what happens is, are the measures we're using accurate? Are they getting at the full range of things? But also our sample, as we saw in the example of the older sample dying just because they were older, right? We want to make sure that we're not missing important pieces of this. I talked about this in my assessment course a couple of weeks ago. But for example, everybody loves to say, well, the SAT is so important because it predicts grades in college, right? It does, but only for the people who get into and go to college, right? You can't look at college GPA for the people who don't go to college, right? So we're missing a huge part of the population and drawing that conclusion off of what's sometimes called the ceiling effect, where you only get sort of the people who are doing the best anyway. And you want to make sure you don't make errors in generalization. You can't just assume that what you found in 100 or even 1,000 people in your particular sample is going to apply to everyone beyond that. And this is why one of the most important sections of any academic article you write is actually the limitation section, where you acknowledge, hey, our sample might be different than the general population for these reasons, and we need to try to study more diverse samples in the future. Or maybe our sample is representative, and therefore our conclusions are different than past conclusions, right? we've talked about this before, but if someone has a figure, we always want to look at those axes on the chart. So basically, have we skipped 0, right? To try to make the differences look more obvious, fun, whatever, exciting, right? And the author of the original book actually argues that the y-axis should always start at 0 and we shouldn't jump. That basically, even if we're going up to 1500 and the differences between like 1500, 1200, and 1300, make it 0 to 1500, right? Yeah, the differences will look smaller, but it's more accurate portrayal of what's going on. Beware of small samples. So simply because there are so few people in them, small samples can produce seemingly shocking statistics. You know, if you have 1 or 2 people who just happen to have some sort of abnormality or some sort of quirk, right, that can throw your whole sample off. So you can get these extreme values. And again, this is why those meta-analyses and systematic reviews are so important, because what they do is look at it over time, right? And they look at all the different studies. And okay, let's take all the studies that only had 20 people in them and combine them. Now we essentially have a bigger sample size and we can see over all those different studies, is that important? We know that there's this phenomenon that happens within data in general, not just psychology, called regression to the mean, where essentially all things being equal, stuff just tends to come back to whatever the average is. This is true even with individuals with their weight, for example. So like everybody has what's called a set point for your weight. It's basically like where your weight is supposed to be. And you might lose or gain, but you're going to tend to come back to that set point. We also need to make sure we're looking at all the numbers, not just the ones that show what we want them to show, right? That's really important. We need to figure out important things about the data set that might not be provided, right? One of the initiatives with Open Science is not only making all the articles themselves accessible, but making the data accessible. So you can actually get that person's data and rerun their statistics or look at the other variables they had in that data set. A single number, a single statistic is never enough to adequately describe an entire data set, right? We see this all the time with like political polls. They'll be like, you know, 48% of Democrats, blah, 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 blah. But it's like, who are you getting to be in that sample, right? Were they actually describing themselves as Democrats or not, right? There might be people who vote Democratic, but don't self-identify as a Democrat. A lot of folks my generation, for example, identify as independents, but tend to vote one way or the other. So you need more information and more context, and a well-written academic journal article would usually provide that, but especially like a media report about an article typically will not. We also need to look at what they're saying when they're talking about the average, right? As we talked about in here near the beginning of the semester, average should mean mean, right? Average should mean you add up all of it and then divide it by the number of people you're looking at. But for some reason, particularly with like salary information in the US, we love to use the median instead, which is like that halfway point. And that always doesn't always tell us the most important information, right? So we need to know, is it the mean or is it the median or maybe even the mode? And again, the mode is just the one that happens the most often, right? So the mean and the median income in the US differ by $16,000. That's more than I made as a grad student. Right? It was like the early 2000s and I was making $14,000 a year as a research assistant, right? So that's a big number. It might not seem like it to a millionaire, right? But it certainly seems that way to someone who isn't making very much. And that can mean the difference between being above or below the poverty line, having access to healthcare, any of the things along those lines. You also want to think about comparing to a common baseline, that you're using the same previous or starting value and putting things in context. And so again, sometimes you just get things that were happening 2 years ago when I made this class. And this is, my daughter is obsessed with ocean animals, still to this day. And we were learning about blue whales and, you know, like thinking about how big is a blue whale. And so oftentimes when you see videos of blue whales, they're still impressive, right? They look like this. Now, I think that's a large animal, but there's nothing else in the shot besides the water to give me context of how big it actually is, right? We're not going to get to other whales, things along those lines. And so I looked into how big is a blue whale actually. And it is gigantic. Blue whales tend to, as mature adults, top out around 100 feet long. And so that is, you know, like the length of 747, or buses, or elephants, or I love that they put smart cars, right? Like, and you can kind of see in context next to some of these things, right? Okay, so we're getting the impression it's very large. This is the one that got me when I found this graphic online. So this is the blue whale. Right, this is the orca or a killer whale. So if you've ever been to SeaWorld, right, you've seen these, they seem big, they're kind of tiny, next to the blue whale, right? But then they put this next to a lot of other things we think of as just being giant. Great white sharks. Minuscule, right, almost, compared to this. The one that got me is that this is a Brachiosaurus. When I was growing up, this was the longest dinosaur. They've now found much, much bigger ones, right? It's like half the length of the blue whale. That's the one that blew my mind. Because growing up, you think like, oh, the dinosaurs were the biggest things that ever roamed the earth. Well, true, the earth, right? But blue whales in the water. And so you think about something like the T-Rex being so intimidating, or the Triceratops, and again, they're not very big when you look at it in comparison. I'm not going to be able to pronounce this one just because I can't read it. It's all blurry, but it's like the Hippopotamus, which is one of the, I think, was the largest flying creature ever. Okay, nothing. And even something like sort of these prehistoric creatures we think about underwater, they're not as big as the blue whale. And so having that baseline, having that comparison helps you to put in perspective just how mind-blowingly large these animals actually are, right? If I say 100 feet, you can like kind of visualize that. If I can say it was twice as long as a Brachiosaurus, you can like have your mind blown, right? And so we need these points, we need these comparisons in order to be able to understand things. So it kind of goes back to like the clinical versus statistical significance we talked about before, right? So like, I can say, yeah, there was the statistically significant difference between these two groups when they went to therapy, one who didn't. But if we look at the baseline and we compare them, and like one of the groups moved like 2 points on the depression scale and the other didn't move, it's like, well, is that actually like meaningful for this person's life, right? We want to see a lot more change typically. We also want to be aware of any existing bias in our sample size. So again, we want to look at how were participants recruited and some of the things we've talked about in here before, right? If it's an internet study, a lot of people don't have access to internet still. If it's a phone-based study, a lot of millennials don't answer their phone when it rings. It's weird. It's true. We want to think about how these might result in biased samples, right? If we're only recruiting from college students, right, we're missing people who are not college eligible or able to afford college. And this weird bias that keeps going up. This is something that is in a great majority of data sets that you look at. So it's Western educated, industrialized, rich, and democratic countries. People from those countries are what we see the most. That being said, we are starting to see more movement from other areas. So like China in particular has really stepped up their game in terms of psychological research and other areas as well. But like, for example, for the meta-analysis that I'm hopefully gonna get published next year, we have over 150 studies, and I believe 2 of those were done on the continent of Africa. Like, they're just not being studied. We also need to think about bias in choosing our sources, right? Do we want to only look at literature that supports our view? Or should we bring in stuff that shows, no, it's the opposite? And in fact, you can build a really good introduction to a journal article you're writing if you say like, hey, so a bunch of people have found this, but then some people have found the opposite. So this is still a question we need to be asking and trying to figure out the answer to, right? But a lot of people will sort of ignore the other side, and it doesn't make for a good argument. We also want to scrutinize authority, right? We don't want to assume that just because someone's a big name in science or a big name in psychology, that means that their study is better than someone who's not a big name. We also don't want to assume that just because research is from Harvard, it's better than research that might come from Virginia Wesleyan, right? Those big names can give it an air of credibility, but what can happen sometimes, and I'm not even joking about this, is that the famous name will be minimally involved in the publication, in the publication of data, and the writing it, and they're just asked to be an author to give it that air of credibility. So then you need to be skeptical, right? Sometimes researchers have been paid to lie, which is sad. They're not supposed to do this. This is a clear violation of ethics. But people will give them, so like cigarette makers or the drug companies during the opioid epidemic, still ongoing. You just think about how many of those drug companies are getting sued, how many times, right? For how they were pushing opioids. Right? Again, good ethical researchers will not do this. And in fact, there are many cases of this happening. I think I gave you the example earlier in the semester of the study that was funded by anti-vax folks that found that vaccines have not the harmful effects they were thinking, right? That is an ethical publication, right? But some unethical researchers will like take that money and do whatever. Actually, where I did my internship at Medical College of Georgia, they had a policy that they didn't accept money, pens, lunches, anything from pharmaceutical companies because the person who had been chairing the department a few years before I got there had been taking that money for his research and just pocketing it. So they made a department-wide policy that like, nope, we're not even gonna have that temptation. So what you want to always do is read the study. Is the science sound? Is it making sense? Is there anything that makes you kind of like raise your eyebrows? Like, I don't know if I would have done it that way, right? authorities should have to prove themselves like anyone else. So I have a lot of loyalty to my main organization that I belong to, the Association for Behavioral and Cognitive Therapies. But a few years ago, they did something that really ticked me off. They made, so when you want to present at a conference, you have to submit. And then there's like, in addition to putting in your proposal, you also like check a bunch of boxes about your demographics and things like that. And they put one on for whether the person was well established in the field and gave that priority. They thought that if they got like famous people to present, more people would come to the conference. A couple different problems with that. Who do you think are the established people in psychology? What are their demographics like? What do you think about it? Just like the numbers of people in psychology that we've looked at. Yeah. White males, they're older white dudes, right? And like white women are starting to establish themselves more, but yeah. So here's an organization purporting that they want to support diversity and they're prioritizing this. A second big problem with this is, again, the assumption was people will come to see these famous people. Well, most students and academics cannot go to a conference unless they are presenting at it. So for example, even for me as a faculty member, if I want to just attend a conference and not present at it, BWU will only give me $300 to attend. If I'm presenting, they'll give me up to $1,500. You might think that's a lot of money, but some of these places to present at conferences, your registration fee for the conference itself is $300 or $500. You have to fly to wherever it is. So my main conference is in Seattle in November. So those flights, unfortunately, I could not find an affordable one. Then you're paying for hotel, food, what have you, right? So if you are prioritizing the established people, you can probably pay out of pocket to go, right? And not giving people who are early career or students the presentation opportunity, then they can't come, right? Because they're not going to get the funding they need to be able to attend. And so it was just so funny when I like brought that up. People were like, really? Like, do you not understand how this works, right? And then again, obviously, you are then devaluing scholars of color, scholars of minoritized genders, right? Scholars who come from outside of the US, things along those lines. So there are lots of different things we need to be aware of and careful of as we think about interpreting stats. And so this is, they called it the 7 deadly sins of misinterpreting your statistics. So again, assuming your small differences are meaningful, you want to look at whether that's clinically significant, whether that's going to make a difference in a person's life. And you want to also make sure you're checking what's called the margin of error. Basically, any statistic we find, any data set we have has error in it. And there are ways statistically to figure out how much error is in that data. What will happen sometimes is you'll find small differences. Actually, I can draw this. So, you know, you might find differences that look like this. And then if you include your error bars, right? I got this much error, right? Basically, if I draw across with the error bars, these are overlapping, right? In political polling, we call this a statistical dead heat, where basically the margin of error overlaps the difference. But for some reason, when we're doing scientific data, we forget this sometimes. And we're just like, yeah, look at this difference, it's great. But in fact, if you take the error into account, it's not actually a difference, right? And we've been talking a lot about statistical versus clinical significance, which is also sometimes called real world significance. So I'm going to show this video here.
Statistical significance is not the same as clinical significance. That's the take-home message of a recent study looking at the outcomes of past cardiovascular trials. Researchers should look beyond point estimates from statistical tests when reporting clinical trial results, say the authors. Instead, the range of possible results, as defined by confidence intervals, should be considered when making clinical recommendations. Investigators often use statistical tests to decide if an outcome is significant. For example, does a medication significantly improve patients' health compared to a placebo? Does a new surgical technique lead to a significantly better outcome than the treatment currently being used? In the literature, the answer to these questions is often given as a p-value, a single figure indicating how meaningful the results are. But what happens when the effects of a treatment being considered fail to show a significant result? Should physicians shy away from these therapies? Not necessarily, suggest the researchers. Such treatments may still have clinical relevance. Sifting through thousands of published clinical studies, the team of Canadian researchers focused on cardiovascular trials, comparing study design, p-values, and primary outcome findings. They found that almost 3/4 of trials reported a non-statistically significant result. According to the new study, however, 60% of these cases had potentially important clinical implications, despite statistical analyses finding them to be non-significant. Just because a medical treatment does not reach statistical significance does not rule out the possibility that it may be beneficial or harmful. By failing to look beyond p-values, researchers run the risk of missing potentially useful results. The fix? The research team suggests authors of future studies take a broad view in which all data, including potentially meaningful effects, are considered when making clinical recommendations.
So I really liked that one because it pointed out that even if something's not statistically significant, it can, in theory, be something that could be helpful, right? And so we need to keep that in mind too, rather than throwing out results if we don't have statistical significance. You want to do things like look at the effect size, and you can compare those across studies. And think about what the difference means practically for the people experiencing it, right?
Statistical significance.
We also want to make sure we don't forget to look at the extremes, or whether we're even dealing with extremes, right? So, for example, I've seen a decent number of studies where when they study something, they rule out anyone who has a psychological disorder. Well, that's like 20 to 30% of the population. Are we really saying we don't care what happens to those folks, right? Or they're doing a treatment study and they rule out anyone who has any kind of disorder beyond what they're looking for. So let's say it's a substance disorder study. They might rule out anyone who also has depression or anxiety. Well, you've ruled out a very meaningful group of folks who use substances, right? We actually know that it's very common to use substance abuse as a way to like self-medicate against those things. So that's problematic, right? And we need to be thinking about, are we studying these people and how to help them? We also want to trust coincidence. Sometimes stuff is just a fluke, right? Those illusory or spurious correlations we looked at. Just because two things happen at the same time or have similar patterns doesn't mean that they're causing each other. Right, and so it can be really easy if we find like a weird correlation to be like, wow, I found something like really groundbreaking. We probably want to test it again in another sample to see if we find the same thing. Again, thinking about causality in both directions, right? Studies say that eating dark chocolate helps your heart. Is that actually true? Or is it that the people who are in good heart health have good insurance and can afford to buy the fancy dark chocolate, right? Or is there a third thing going on? We also want to make sure we're considering those confounding or extraneous or lurking variables. always trying to think about what else could be at play here.
And then I switched to Liberty Mutual and saved hundreds. I know, exactly.
Fortune is my best friend. Hey, when it comes to writing, and I'm not.
As epidemiologists, one of our main objectives is to investigate relationships between exposures and health in populations. However, once identified, our challenge is to determine whether this relationship represents a causal pathway. In other words, does the exposure truly cause the outcome? If we're not careful, we may incorrectly conclude that causal association between two factors exists. This occurs because the association we observe is distorted by another factor that we have not considered. We call this distorting factor a confounding variable. Confounding is one of the most important problems in epidemiologic studies because it results in spurious or distorted associations being observed. A classic example of confounding involves the investigation of an association between carrying matches and lung cancer, where researchers concluded that people who carry matches are more likely to develop lung cancer. This is, of course, not the correct root cause. The factor not considered here is smoking status. Smokers are more likely to carry matches and more likely to develop lung cancer. But since smoking status wasn't considered, it appeared as though carrying matches was the exposure that led to a higher likelihood of developing lung cancer. So we would say that smoking status confounds the relationship observed between carrying matches and developing lung cancer. As epidemiologists, we must carefully consider what factors might potentially confound results. And when an association is observed, we must assess whether a confounding relationship exists. To do this, we consider whether a potential confounding variable meets three criteria. The confounding variable must 1. Be associated with exposure of interest, 2. Be associated with the outcome of interest, and 3. Not be a result or caused by the exposure of interest. This final criterion is about temporality. In other words, which of these exposures came first? If the factor in question meets all three of these criteria, it is considered a confounder. It can be helpful to draw the factors of interest out in what's called a causal map, and then work through the three criteria. A causal map is a bit like a timeline, where time moves from left to right. We put the exposures on the left and the outcome on the far right. We then consider whether the potential confounding variable would sensibly occur before or after the exposure, and place it on the map accordingly. Let's try an example. Say we're interested in the relationship between getting the flu vaccine and the likelihood of getting the flu in the same season. Now we're concerned that participants' occupation, such as being a health professional, might confound this relationship. On our causal map, we place occupation furthest left on the diagram because it precedes getting a flu vaccine. Now we investigate for confounding by first asking, is the potential confounder associated with the exposure? In this example, yes, health professionals are more likely to get the flu vaccine to decrease their chances of getting the flu. Next we ask, is the potential confounder associated with the outcome? In this example, yes, health professionals are more likely to get the flu because they are exposed to high numbers of sick people. Finally, we ask, is the potential confounder caused by or a result of the exposure? In this case, the answer is obviously no. One does not become a health professional because they receive the flu vaccine. Therefore, we can conclude that occupation is a confounding variable of this relationship. Confounding can be a major source of bias in epidemiologic studies, bias that leads to spurious conclusions about a given relationship. Therefore, it's crucial that we critically evaluate the associations we observe, using the three criteria for a confounding variable and causal mapping to ensure that we are aware of potential confounders and address them within our studies.
I love that because we think of epidemiology as more of like a hard science than psychology, and they have to think about these things too, right? So that becomes really important. And then deceptive graphs, we talked about in passing, and we're going to talk about in a lot more detail next week. I'm going to stop there. And let me real quick just remind everybody where the assignment from the other day is and what it's about, and give you guys about 10 minutes to work on it in here. So if you go to our Blackboard page, and you go to assignments, you can find the one on bias in sources, and that's the one we're working on. If you click on the link, it should open a copy. If you started working on it the other day, you may have one already. I'm going to go ahead and throw this in the Zoom for our Zoom folks. But the rest of you can, and Zoom people can, just find it. And then, yeah, you can work on this. So again, reminder as to what this looks like. It's gonna ask me if I want to make a copy. Yep. You're finding 2 additional sources, so not the same ones you did on the last source assignment for your topic. And then you're gonna cite each one and answer some questions about the study in general, but also in particular, what kind of bias do you think there might be? So if you did happen to finish this the other day, you can head out, but if not, you can use this time to work on it some more. And folks on Zoom, I'm going to stop the recording since we'll have some dead air, but I'll be here in case you need to ask any questions.